All right, let's wrap up our introduction to chemistry by talking about one last conversion, and that is converting to the proper units in temperature. Okay? So temperature is probably not a new topic to you. You often, ask for the temperature when you're going outside, whether or not to put a jacket. So sometimes we think about temperature as being a measure of heat, but in reality, it's not a measure of heat. It's actually a measure of the energy of molecules. Okay, so if something has a high temperature, the molecules of that substance have more energy. If it's a low temperature, it's low energy. Okay. And what chemists use to measure temperature is called Kelvin. Kelvin's our SI base unit for temperature. Okay, Kelvin there. And maybe you're not used to that unit. Maybe you're more familiar with Celsius or Fahrenheit. And generally, those are not good to use for chemistry because those don't quite measure the energy associated with molecules. How can something have a negative temperature, meaning it has a negative energy? Not quite. So Kelvin actually measures the absolute temperature. And what that means is that it measures the energy. This measures the energy of a substance or any matter, and it measures the energy of the matter. Okay, and at 0 Kelvin, that's when all particle motion is going to stop. Okay, so that means there is 0 energy available. Okay, and that's why we prefer Kelvin. It's referred to as an absolute value, There's no negative Kelvin. Once you get to 0 Kelvin, that's when all motion will stop. So we need to know how to convert in between what we know normally, which is Celsius, and convert that into Kelvin. And it's a really simple conversion. We just add 273 to any Celsius value that we may have. Okay, so let's look. Imagine we want to convert this 39 degrees Celsius into Kelvin. We simply just do 39 plus 273, and that's going to equal our value in Kelvin of 312 Kelvin. Okay, and there you go. There's your answer. I do want to point out that normally, we have to take into account our significant figures when we do any kind of mathematical conversions. But in this case, we're converting an absolute value from one to the other. This 273, okay, is as an exact value. So you don't have to consider it when you are doing your significant figures. As scientists, we often collect data, and you want to know if your data is good or if it's bad. And one way you can kind of analyze your data is by looking at its accuracy and its precision. Okay, and these have two different kind of meanings: accuracy and precision. Accuracy is going to be how close a measured value is to the accepted value. How close you are to the accepted value. Okay. You could take that measurement 1,000 times, and if you get one that is very close to that accepted value, you're pretty accurate. Okay. Precision, on the other hand, is how close a series of measurements is to each other. Okay. So it doesn't matter if you are close to that accepted value, but if you're close to a similar value every time, all 1,000 times you take a measurement, what we call as being very precise. Again, let's get an example of what this might look like. Here we have a student that collected data in an experiment. If the true temperature of the sample is 45.4 degrees Celsius, is the student's data accurate, precise, both, or neither? Okay. So in order for it to be accurate would mean it would be very close to this actual value, close to actual value. And if it's precise, that means that all of the data points are close to each other. So we have 3 data points, 45.5, 49.2, and 41.3. Are any of these close to the actual value? Are any of these close to the actual value, which is 45.4? Well, yes, this trial 1 is very close to our 45.4. So our data is definitely accurate. All we need is one value to that actual data point in order for it to be considered accurate. Are these 3 values close to each other? Are they close to each other? I'm going to say kind of, but they still have about 4 in between each of them. So I'm going to say it's not precise. So in this case, our data would be accurate, but not precise. Accurate, but not precise. Another way that scientists analyze their data is by calculating the percent error. How far off were you from this accepted value? Were you close or were you not really close at all? All right, so let's see how we calculate this. And it's a really simple equation. We're going to take the absolute value of the accepted value minus the experimental value and divide that by the accepted value multiplied by 100. Okay, pretty simple, percentage calculation. So let's see what that looks like in practice. And if a student demonstrated the density of an object to be 1.36 grams per centimeter cubed, calculate the percent error given that the true density is 1.59 grams per centimeters cubed. Okay. So in our case, we know that the accepted value is this. This is our accepted. And that our experimental is this. That's our experimental. Okay. So we're going to plug those in. 1.59 minus 1.36. Take the absolute value of that difference and divide it by our accepted, our 1.59, multiplied by 100. Go ahead and plug that into your calculators. You should get 14.46%. We're going to round to using our significant figures. Oops, I'll round up here. 14.5%. Final answer there. So that means that our experimental value is 14.5% away from our accepted value. Okay. Generally, a lower percent error is going to be better. The lower the percent error, the better. Another way that scientists really analyze data is by graphing it. And these graphing is a visual display of data. Okay, graphing is a visual display of data. And this allows us to really see patterns. Humans are definitely visual creatures, and we like to see things. And graphs give us a very easy way to do that. Okay, and all graphs must have a few things. All graphs must have a title. Okay, we have to, and all graphs have a x and y axes. The x is going to be horizontal while the y is vertical. And you should always have, we'll put the title for our graph up here, title. And these axes should have labels on the side. You should tell someone what the variable is. And often our independent variables being put on the x-axis, and the dependent, what you're measuring, is put on the y-axis. And lastly, we need a scale, and that just means you need to either display how a change as you go down the x-axis happens, and that scale is demonstrated by the units here. Usually, you put 0, 1, 2, 3, etc. Okay, so you need to make sure you label it. You also need a scale. Let's look at the three main types of graphs. There are many types, but these are 3 basic ones. The first is a line graph, and you use this when you have numerical data on both axes. So here you're going to graph a number versus a number. Here's an example of a line graph. You can look on the x-axis down here. We have the amount of fertilizer, and on the y-axis you have the height of a plant. Okay, so here we are going to graph our numbers versus numbers, and that's why it translates nicely to this line graph. Next type is called a bar graph, and we use this when we graph our categories versus numbers. Categories versus numbers. Ooh. Categories versus numbers. Okay, so for example, this bar graph has the type of candy bar. This is our category here. And our number of students is going to be on the y-axis. All right, and this is a proper bar graph. It's called a bar graph because there are bars that kind of indicate how many land in each category, and in this case, the types of candy bars. Third type of graph is a circle graph, and we use this when we're graphing a percentage of a whole. Okay, so the entire circle represents the entire amount, the entire group of people or things, and each sliver or slice of the pie is going to represent a certain percentage. So in this case, our homework represents 23%, our games represent 15%, and so on and so forth. Scientists often use these graphs to interpret our data. That means we draw conclusions, we find patterns, identify trends. Okay? And this is important because we need to make predictions for the future. Okay? What will the future actually hold? We can't really tell for sure, but we can use our data to make these predictions. Okay? And that's really what scientists do. Okay, this is our best guess for the future, or you could say your hypothesis. If you're a mathematician or you want to do a rate of change over time, you could also calculate the slope on a graph. Last topic we're going to touch on, we've talked about this a little bit already, but that is density. Okay, remember, this is another physical property of matter. This is another physical property of matter. Physical. Okay. And density is defined as a ratio that compares the mass to its volume. Mass to its volume. Okay. And what that means is that density is simply the mass of an object divided by the volume of an object. Okay. And the units for density are always written in grams per milliliter or grams per centimeter cubed. Okay. Grams per centimeter cubed happens when you have a solid substance, and grams per milliliter is for a liquid or a gas substance. Okay? And note that this conversion always holds true. 1 milliliter is always going to be equal to 1 centimeter cubed. All right, let's look at an example to see how we can use our equation for density to kind of calculate an unknown. Right? And this example says we have a piece of metal with a mass of 0.147 kilograms. And that metal has a density of 1.25 grams per centimeter cubed. This asks, what volume will the metal occupy? Okay. So we know that density is going to equal the mass divided by the volume. We also know that our density is 1.25 grams per centimeter cubed. Our mass is 0.147 kilograms. And our volume is going to be our unknown. You'd think we could just plug this into our equation here, but we need to make sure that our units are going to be equal. Okay, and so we're going to do a quick conversion using dimensional analysis before we begin. We want this to be into grams, so they match. I'm going to take our 0.147 kilograms. I'm going to divide 1 kilogram, 1 grams on the top. That means we have, if we multiply across the top here, divide across the bottom, we should get 147 grams as our mass. So 0.147 equals 147 grams of our metal. Now we can plug into our equation. Our density is 1.25, and we know that's equal to 147 divided by our V, our volume. Okay. We do some quick algebra, and we know that we can set the volume equal to 147 divided by 1.25. We're going to plug this into our calculators to get our answer for our volume. You should get 117.6. Our units here in this case are centimeters cubed. However, we need to make sure we have the correct number of significant figures. Our answer only gives us 3, so our answer should only give us 3. Our question only gives us 3, so we should have 3 here. This is going to round up to 118 centimeters cubed. Let's look at another example here, and this time we have an irregular shaped toy that's placed in a graduated cylinder. The water level rises from 30 milliliters to 36 milliliters. The toy has a mass of 2.5 grams. What is the density of the toy? So we're using a method called displacement here in order to find our volume. We have our grams, we have our mass right here. We don't know the density. We have our mass that's going to be equal to 2.5 grams. Our volume is some kind of unknown. We need to use these values in order to calculate that volume. Okay. And we use what we call displacement here. So we have 2 or 1 graduated cylinder. Before we put the toy in, it's got a volume of 30 mils, and then it's going to go up. It's going to start there and end up at 36 milliliters, and imagine the toy is down here in the bottom of our graduated cylinder. So that displaces this amount of water right here, which we can calculate as 36 milliliters minus 30 milliliters to get the difference of 6 milliliters. Okay. So we use displacement to calculate our volume there. And now we can just enter this into our ratio. 2.5 grams divided by 6 milliliters should give us our answer. 2.5 divided by 6 gives us 0.416 repeating grams per milliliters. Nearly done. We need to make sure our answer matches the number of significant figures. Okay, in this case, our lowest significant, our least precise value only has 1 significant figure. So we're going to make sure our answer only contains 1 significant figure. Our answer becomes 0.4 grams per milliliter. Density can also be used as a conversion factor in dimensional analysis. Okay, we can use density as a conversion factor, and let's see what that looks like. Okay, we have a kitchen faucet that needs to be coated with 1.5 centimeters cubed. That's our key that we have volume. The density of the chrome is 7.19 grams per centimeter cubed. Calculate the total mass. Okay, so we're going to do our same density ratio calculations, but in this case, we're going to use dimensional analysis. So we need to set up our train tracks, and we want the mass, and we want to measure mass in grams. So that's what we want on the end for our answer. In this case, we are going to start with our given. We know we have this much chrome, 1.5 centimeters cubed. Okay, and we use our density as our conversion factor. So what this is essentially saying is that for every 7.19 grams of chrome, that's going to equal 1 centimeter cubed. Okay. We want our centimeter cubed on the bottom. I'm going to put the 1 down with it. Put our 7.19 grams on the top. Okay. Now it's just a simple multiplying and dividing. So in your calculator, you should put 1.5 times 7.19 divided by 1. And that's going to equal our answer. And in this case, you should get 10.785 grams. Okay, we're nearly done. We just have to make sure our answer matches the significant figures for the smallest to least precise value. So this is going to round down to have only 2 to 11 grams of chrome.